Good afternoon. Welcome to this really unique and interesting opportunity here we have, where we've got a talk about architecture in the School of Forestry and Environmental Studies, and this may be a first, I'm not sure, but we've had the great pleasure to have with us today two architects who are leading the initiative to build tall buildings with wood as structural materials. Michael Green, who is from MGA, Michael Green Architects, is a firm he's just started. He left his old firm, a couple of weeks ago, and has just started a new firm. He's in Vancouver, Canada. And he's put out a document called The Case for Tall Wood Building, which I'm sure you'll hear more about during his talk, which has really got the airwaves fluttering about what things we can and cannot do with wood. And our other guest is Andrew Waugh from Waugh Thistleton Architects from London. He and Michael and I met in Bangalore, India at the FAO conference on the joy of wood. And when I heard the kind of work they were doing, I immediately invited them to come here to Yale. So I don't think I need to say much more in the line of introduction. Welcome. We're very glad to have you and look forward to your talk.
Oh, really?
Yeah, we have to use these guys. So we're gonna tag team this presentation, but it's a huge pleasure to be here. We've had a really fun day already, and for me, it's really special because I spent 8 years living here in New Haven, almost 9 years. So it's pretty great to be back. I've been in Vancouver for the last 14, so it's pretty nice. Andrew and I end up lecturing a lot together around the world because we're in this unique conversation we're having, and so that we're going to talk about tonight. But it's great fun because we get to come together. Andrew's practiced in London. We get to come together and sort of share our current work and the issues we're looking at and learn and grow from each other. So this is a pleasure just to be able to get to do this together again. It's been since, I guess, when we were in India with Mary, since we last did it. So we're going to tag. Andrew's going to start, and
you just started already.
We're kind of, we're.
I feel like I should break into song.
I know, it feels funny with the microphones.
So if I do, then please.
Actually, you know, one question, just for, because it is interesting as architects for us to be here. Is anybody in the room an architect? Who are we looking at? 1, 2, 3, 4. Okay, and everybody else forestry or general public or forestry hands? Landscape architecture, excellent.
Yeah.
Building official. Uh-oh. Excellent. How about engineers? Anybody engineer? Yeah, good. Okay. It's a crowd.
Great. Do we flick this forward? Yeah, okay. Okay, so what we're going to talk about this evening is the principle, the idea that wood as a viable alternative to concrete and steel. So the work that Michael and I are doing is not principally looking at timber, at wood as an aesthetic material, but timber and wood, the idea of it being an alternative, or the principle that it can be and should be seen as an alternative to concrete and steel. So why wood? This is where we start from. This is where the essential kind of the crux of the problem comes from. 7 billion people, which was the big news at Christmas. So when we were born, weirdly within a couple of weeks of each other, and you have to guess who's the oldest, but we can leave that to this, there were 3.5 billion people on the planet. So this is our problem. This is our generation's problem. This is for us to deal with. That's 3 billion people will need a home by 2035, 100,000 homes a day. So this is for our profession, for our industries. This is the problem of our lifetime. Of these, 70% will be urban by 2050. If we have an understanding of the fact that to house all these people in order to be able to live in societies which can function adequately, we need to densify our cities. So we're looking at and understanding dense urban contexts in order to be able to house these populations. And how we do this, because the building industry itself, as we stand, is responsible for 40% of the consumption of world's resources. And here, what I've done, actually, rather than saying 25% or 40%, it's giving you a range, because I don't know, when any of us research these things, you can go to the concrete lobbying organization and they will say one figure, and you go to Greenpeace and you get it right on the other end of the spectrum. And people are quoting these all over the place. So what we've done here is to use some figures within ranges of these kind of quotes. So for this one here, 25 to 40% of the consumption of energy on the planet is from the construction industry, from the building industry itself. 30 to 40% of the emission of greenhouse gases is from construction. And 30 to 40% of solid waste generation. Now, as we stand, the building industry itself principally uses concrete and steel for these buildings. Concrete itself is responsible for between 5 and 8% of global greenhouse gas emissions. So that makes it the fourth single biggest emitter of greenhouse gases. Steel for 4%. So per volume, in terms of the construction industry, the biggest emitter of greenhouse gases. Now, this is compared, importantly, to airline travel, 1.6%, shipping 3%, and again, concrete 5%. So if you build in timber, you can fly where you like. Get used to my humor.
So now we're going to switch over, and I guess this really is the essence of how both of us came to this discussion. I come from BC, where it's obviously a big timber industry, so it's an important discussion in my community. But my interest as an architect, and Andrew's interest certainly, is around the issue of climate change, around the issue of environmental footprint of the buildings we build, and looking for a new responsible way. So much like Andrew suggested, is that the fact that the world is urbanizing at this extraordinary rate means that we need to not look at solutions that are rural or suburban scale, which much of the architecture industry has been looking at for a long time, of greener solutions. We really need to look at the big buildings we make. And again, the bones of those big buildings is really where we found we need to start from square one. So effectively, in all those statistics, and to go one step further on the stats that Andrew just talked about, here in the United States, it's almost 50% of greenhouse gas emissions are related to the building industry, and almost 50% of energy is related to the making and manufacturing and operating of buildings. So those numbers are actually slightly skewed down worldwide as they are here in North America. They're even more extraordinary. So obviously to us, the reality is that big problems equals big opportunities equals big solutions, and that's really why we've sort of stepped into the fray of very, very large kind of systemic change discussions about how we build in urban buildings. Largely, all of us are thinking greener today. And I always love to use this quote: I put my money on solar energy. I hope we don't have to wait for oil and coal to run out before we tackle it. And the great thing about that quote is Thomas Edison said it to Harvey Firestone and Henry Ford, and he said it 80 years ago. And the thing I like to point out is that, of course, as we are all working hard to now build greener buildings and add photovoltaics to our buildings and other green building systems, the reality in what we do ultimately is that the only building material that we really build with in large quantities anyway, that is fundamentally grown by the sun is of course wood, which becomes a very easy moniker for why we want to do this. But ultimately isn't the issue that when we put all this energy, all of this process into the basic building materials of steel and concrete, really ultimately we're trying to compete with photosynthesis, and we don't have a prayer keeping up with it. So fundamentally we need to look to solutions that take that advantage. And some of you, certainly the forestry industry, know this, or the forestry school know this statistic, but that fundamentally, unlike concrete, that 5 to 8% emitter of greenhouse gas, and steel, wood, on the other hand, has that great capacity to not only use less energy to be turned into from a tree into lumber, but also has the ability to sequester carbon at the rate of roughly 1 cubic meter, storing 1 ton of carbon dioxide. So not only are we not putting it into the system with our structural system, we're looking at how we can ultimately store it and change the whole dynamics of buildings. So obviously wood is a renewable resource, and that ability to sequester carbon are the two critical components that really begins our conversation tonight. The other big starting point is really to say that when you look at a map like this, it's the UNFAO's net change in forest area, and when you look at it, what we have to recognize is these ideas as important as they are, they also can be detrimental if they're not managed in an appropriate way. So if we don't source the wood we're going to talk about in from sustainably managed forests, we're really doing a great disservice. And what we'll see likely is that in different parts of the world, these issues will be more challenged than others to do that. Here in North America, in Europe, we have the chance to source from reasonably well-managed forests, or very well-managed at times. But obviously the southern hemisphere, where you see all that red, is of great concern that we don't exasperate the issues of deforestation. And so every time we talk about it, we underscore that this is an important beginning. So kind of stepping back, and why is it that we're here today and looking out at the cities that we all are used to living around? Why are they built the way they are? And obviously the answer to that's really the Industrial Revolution. The sort of onset of wrought iron and ductile steel, the introduction of concrete and being able to move it en masse, and the Industrial Revolution allowed us to reshape the skylines of every city on Earth. And now at this point, every city on Earth largely is starting to look the same. We build the same way everywhere with those two materials. And the big change is what we just talked about. The only reason to start over in reinventing the wheel, essentially, on tall buildings is ultimately the issue of climate change. And that's why this is a new conversation that we're trying to have. It's really only the last 10 years, as we all start to get our heads into it, that this even becomes an appropriate conversation. Steel and concrete are great materials until you consider their footprint. And the other reality is what's happened over the last 100 years is, although 100 years ago we were able to build very significant large wood buildings, and historically, even dating back a lot longer, we built large wood buildings. What's happened over the last 100 years is our building codes have slowly actually taken away and actually capped the limits of what we were allowed to build. So in this diagram here, this is a 4-story wood building based on the maximum we were allowed to build in British Columbia. Again, a very progressive wood culture. But that was as tall as we were allowed to build in wood. And a couple years ago, they changed that to allow 6 stories in 2009, which was, I think, the first in North America to allow us to go to 6 stories. And what they were imagining is taking 2x4 kind of construction and going bigger. But by the time we passed that 6-story change, my good friend Andrew here had already built, is that date right, 2008? That had already built a building that he'll talk about in a minute, this 9 stories tall in London. So our building code in Canada, which was the most progressive in North America at that time, was still not even catching up with what Andrew had already done, which is very frustrating when you want to create these ideas. But more importantly, the way I always tell this story is I was riding my bike with my son across Japan, and I had got a text message from the office saying, hey, it's really great, 6-story code just passed in BC, isn't that exciting? And I quickly emailed or texted my office back and said, that's great, guys, but I just came out of a building this tall, and more importantly, it was built 1,400 years ago in a high earthquake zone, in a wet climate like BC where I live, and yet, if we could do it 1,400 years ago, why can't we do it today? And the fact is, no place on Earth, largely no place on Earth, has a code that actually understands and accepts the idea that we would ever consider building that big today, with some slight exceptions in places like the UK. And you know, frankly, there are many places like Russia has a cap on 3 stories. Some places, Switzerland not long ago had 2 stories as maximum. So I guess what that comes to is the idea that we are at a moment in time, a real transformation in time in the way we build, and that in some ways it reflects the era of Gustav Eiffel, and that when he stepped out for the World's Fair and said he was going to build this building in wrought iron, at the time city councilors didn't like it. Many city councilors in the city of Paris said, okay, we'll let you build it, but you have to tear it down 5 years from now because it's such an ugly eyesore. And of course today it's the symbol of France, and it changed the way many people imagined what was possible. What in turn happened, of course, is what we all know, is the great race that happened from city to city around the world to build high. So the Chrysler building was going up in New York, and then the Empire State Building had to be taller. And what that was doing was pushing our engineers, pushing our thinking and our imagination to the ceiling so that we basically shape the cities now that we're all used to, such that we never walk by a 60-story tall building and sort of think it's going to fall down on us. We became accepted and accustomed to it. And yet, strangely enough, with wood, and we're going to get into it in more detail, the opposite's happened. We've become, over the last 100 years, our idea is that you can't possibly hold up a big building in wood. Well, my office that I just moved into just a week and a half ago is a 105-year-old building, heavy timber, and 8 stories tall. 8 stories measured from the parking garage with big, giant, solid timbers. Obviously, we were doing it 100 years ago in many places, not just my office, and yet we've lost that sort of sense of opportunity. So the great thing is the race is on. So right there is the 9-story one is Andrew's building, Murray Grove, but there's proposals in Norway, there's a proposal in Austria, there are proposals happening all over the world now for us to start creating the race and build real buildings at these heights. I can't remember where we transitioned. We're going to find out in a second. So really, basically, I think we are going to transition here. The change starts with the materials.
So we're going to talk to you about mass timber, which is the material that we're both working in, which is massive engineered timbers. So these are large, like we're here today looking at the glue lams above us here, LSLs, which is laminated strand lumber, laminated veneer lumber, LVL, glue lams, and CLT. CLT is the material which my office has been working with principally. CLT is a very simple, very straightforward material. It's secondary grade timber planks, about an inch thick by 3 inches wide, and they're laid out and glued using a water-based PVA adhesive, and then cross-laminated against each other. So laid out at 90-degree angles. So it's like a jumbo plywood is what we're talking about. And then those panels come out of the factory at about 50 feet by about 12 feet wide, and then a CNC cut to the appropriate shapes for their use. So talk to you about a case study, and this is my office. This is us. This is the cafe in East London opposite my office. This is me here, and this is me here, and this is me here, and this is me over here. So we're a little office that tries to look a lot bigger than we are. So Murray Grove is about 15 minutes walk from my office here. This is the Jolly Roger pub on Murray Grove, which was closed down by the council, and because they planned one too many bank robberies in there, and we got the commission to look at doing an apartment building there from a local developer, from an East End developer. And we had a long conversation with them about the opportunity of building this building in timber, which was an amusing conversation in hindsight. We built a building from cross-laminated timber about 5 years previous to that. And every time a client came in the door, we'd discuss with them the idea or the principle of doing these buildings in cross-laminated timber, or in massive timber. And after years of refusal and years of people just getting up and walking out of my office, we managed to hone this argument down in terms of the argument to be presented. So we have this very clear understanding of the nature of the advantages of building in heavy timber. So we sit the client down, talk to them about this building here. We have I'm going to shine this in my eye, trying to find out which way it is. There you go. Honeycomb cross-laminated timber structure. So every panel is working in this building. So this is a building which we're talking about completely in timber. So the elevator shaft, the stair shaft, the external walls, floor slabs, a lot of the internal walls, all made from massive timber. So the whole thing acts as a honeycomb, if you like, which means that you don't have the same necessity for columns or load paths traveling in direct lines through the building, which means you can alternate the plan across the floors. So this is a decided advantage for our client. So cross-laminated timber has the advantages of like a jumbo plywood, if you like, has the advantages of acting as a beam, that a wall will act as a beam. So the walls are carrying the load from across the length of the wall, and the floor slab will work in both directions. So you have the primary timbers on top and below, and that's your primary load path. And then the timbers in the middle will give you a secondary load path, which makes your slab stiff across the width. In terms of moisture and stability, again, they're very stable materials. So we had a terrible thing happen about last summer, the end of last summer. It reached the dizzy heights of about 75 degrees in London, and we had one of the cladding panels popped off the building and fell onto the sidewalk. want to say narrowly missing a baby, but that's not the case. But we, so everybody, so of course the developer phones me up on the weekend and, running down there, and everybody's like, well, this is just because of the timber system, because of your timber structure. So we had to resurvey the building after 2 years of complete, 2.5 years complete. And on resurveying the building, we found that the whole building had moved over the period since construction by 4 millimeters, which is in metric, I don't know, an eighth of an inch. So boggle, as we say in England. So the sketch that we show our clients, that we discuss with the clients that come in, is to talk about this building instead of a slab and column building, such as you build in concrete, to talk about a panelized system, and that the weight of this building is a quarter of the weight of concrete. So that's the first thing we sit down and we say, look, if we're building a building that's a quarter of the weight of concrete, we don't need a tower crane. We can do the whole thing from the back of a truck with a mobile crane. We need about a third of the amount of foundations on this building. And also, it's fast. It's a very accurate, very easy material to work with, and very, very fast. So we did a comparative program for the client, showing them a concrete frame building going up in about 18 months, and the equivalent timber building going up in less than a year. And in fact, from when we started demolition to when the first people moved in was 11 months. So just in terms of how we built this building, these panels here, this is a diagram showing the panel layout on one of the floors here. So these are the biggest panels we could get through the Channel Tunnel, which are about 36 feet long by about 2.5 meter wide. So that's just over 8 feet by 36 feet. And these are our floor slabs here. So you can see this is a principal low path going from front to back. And then these are the walls here. So these are bedroom walls. And you can see this is the party wall in this situation. So this is one apartment, two, and this is a big 4-bed apartment here. So you can see how they're separated there. So we're able to move these party walls across the structure, giving us that varied plan, which allows us to change the building as it goes up. So on 9 floors, we've got 5 different floor plans on 9 floors. So in terms of fire, the way that it works in the UK is we have a system of compartmentation, which is where we separate out the apartments from each other by having a 1-hour fire separation between each apartment, and then a 2-hour fire separation on the lobby and the elevator shaft. So the idea being is that if there's a fire in this apartment here, then this apartment's got an hour to finish watching what they're looking at on TV, and then to get leave. So just in quick terms, I'm doing this quite quickly so I can give Michael some time to talk about the work that he's been doing. But this is a section through our building here. So this is the floor slab, which is a 6-inch timber slab, and then 5 inches for the walls here. And then we have an acoustic insulation that goes and wraps up the end there. And we have a screed on top, and that's for an acoustic separation, but also gives us a thermal mass as well. So we're able to put underfloor heating in this screed here. And then we have a void, insulation, and plasterboard below here. On the outside of the building here, we have a breather membrane. What do you call that, like a Tyvek kind of stuff? So yeah, breather membrane. So a breather membrane on the outside of the building, and then we run a rail system down that, and we push the insulation on top of that, and then we have a simple rain screen cladding system on the outside, which is made from a wood pulp and cementitious tile. So very simple construction method. Hi, yeah. That's it. That's not schematic. That's a construction drawing painted green. It's a platform construction. So the wall panels sit on the edge of the floor panels.
But there's angles there. Right?
There's a little angle bracket that sits there, and then in localized positions we've got some screws that sit underneath the wall panel here, just for compression, for creep on the edge of the slab. But that's really, the whole principle was to make sure that the building was incredibly simple. The idea was always to get the building built. So to make sure that the building was very simple, so that there were no kind of no complications for the contractor, no excuses for the contractor to say, oh, it's just a far too difficult thing to do. So we made it very, very simple. You can see this is a section here through the lift shaft. So we have a separate a separate panel here for the lift shaft, and these are the internal walls up against there. So you have just a 40 mil, a sort of 1.75" separation between the two. So this should explain it. This is a better idea here. So this is the construction process. So this is our ground floor concrete slab. This is London here. This is my office over there. This is beautiful, isn't it? So the process of construction was that on a Tuesday morning, a truck arrived with 4 Austrian carpenters and some panels on the back. And then on a Wednesday, another truck arrived. On a Thursday, another truck arrived. And on a Thursday night, they went home to Austria and were tucked up in bed. So they built a story in 3 days, Tuesday, Wednesday, Thursday, and they built a story a week. So in 27 work days, we built 9 stories. And you can see no crane here. And that's the finished result. Can I just play it once more?
Is there any bracing needed during each level?
No.
Progress up in height? No.
Bracing for stability or for shear? No, because all the walls are working. So all the shear forces, all the P delta forces, if you like, pass through the slabs, pass through the front elevation and down. Does that make sense? So because the connections run along the length of each one of the wall panels.
So as you progress with the walls, you're starting from corner to the end of the next corner?
Because it's a platform construction, so the first thing that happens is you lay the floor slabs, if you like, and then really the sequence of construction across the building is you start in one corner and you work your way back. You have a series of angles of sort of a temporary propping, which you screw into place to hold the walls at 90 degrees.
So you're raising them up from the floor.
Well, they're dropped in by crane and they're dropped in vertically. Does that make sense?
And you do put in some temporary diagonals for a couple panels to support them until you start making the right angles that hold it together. Yeah, just as you would with light wood frame in that way when you tilt a wall up.
So this is some of the construction here. You can see this is the first fix here running through for the electrics and for the gas lines. And you can see here the connections that we're talking about. So the whole building is put together using 3-inch galvanized brackets at 18-inch centers with 4-inch screws. So that's 3 guys with cordless screwdrivers and 1 guy driving the crane. The argument that we had, the discussion that we had with our developer client about the building was that when we sat him down and we explained to him the environmental and sustainable benefits of building this building in timber, he said, the thing is, Andrew, I don't give a monkeys for the environment. I'm not interested. You're going to have to sell this to me in a completely different way. So we sold it to him on the basis of speed and efficiency and cost. We were cost equivalent to concrete, but we were 6 months quicker. So he said, okay, well, that's fine. We can go with a timber system, but I don't want anybody living in this building to know that this is a timber building because I'm worried that they won't buy it. If they think this is some kind of like sustainable exercise, then they're not going to touch the building at all. So we said, okay, fine. We just want to build the building. So we covered the interior of the building with gyprock here, which at the time is kind of, when you've got the sauna sort of stage here, and then you go to this, it's a little bit heartbreaking, especially being in this sort of situation. But actually, I think that in hindsight, what this has done is to strengthen our argument in terms of proving a viable alternative to concrete and steel. Because the viability of this building has not been about the aesthetic, it's been about the structure and the efficiency of the construction process. So that's actually worked very well in terms of being able to talk about timber as an alternative, using this building as an example. And in addition to that, we leaked it to the newspapers anyway. And before the building started on site, there was a 2-page article in the local newspaper, and which has a circulation of about 15 million. And they'd said that this building was going to be built in timber. And a week later, the building was put on sale off plan, and the whole building, all 29 apartments, sold in an hour and 15 minutes. And they sold to people who cared about the environment. they sold to people who actually were really excited about the fact that the building was built out of timber, and at this moment are busily taking the gyprock off the walls. So you can see here, this is during the construction process, and this is the end of the job. So we have here an inboard balcony, no cold bridging issues, nothing like that. We've got torch-applied felt on the balconies. So I came into the site here, onto the building site, and you've got some Polish bloke sitting on the corner there with a blowtorch in a timber building, putting the felt on, which is a bit of a heart-stopping moment. So there we go, finished product.
Okay, so Andrew's building has been an inspiration for a whole lot of people around the world, including myself. I was a partner in a firm, about 35 people until just a few weeks ago, as Mary said, and I split off my firm. This is move-in day just a week and a half ago into our new space. As I said, this is actually our new space in behind the. Where's the pointer? How do I use the pointer? Where's your pointer? That's better. These in behind here, these are timber columns holding up this 105-year-old building. It's a real pleasure to work in a building like that. It's much like this building. It just feels natural and great. My firm and my practice, I've built things all over the world, a lot of international airports, a lot of wood buildings as well in the last decade. And more as I did that, I became sort of vested in the idea that there has to be this other way around these discussions of climate and so forth, and around the work that Andrew's been doing. What that triggered is something, a sort of attitude, I guess, in my practice and personally, that a lot of the conversation we've been having about green environmental buildings has been either the sort of checklist approach to LEED buildings, which is a good thing, or the sort of tendency for us to kind of create additive buildings. We'll put some photovoltaic panels on the outside, we'll put a green roof on them, we'll sort of add to the building with things in order to somehow create a green argument around the building. And there was this sort of sense that I had some time ago that maybe we actually just need to hit reset and ask the question, are we staring at the trees or are we looking at the forest? Is there a big decision that we could make that would make a more profound change in the way buildings work worldwide? So finding the forest through the trees actually became the name of the system that I'm going to describe now, which is a new way that has just been published to build very, very large buildings. About a year and a bit ago, we proposed and received grant funding to basically set out with some engineers, some cost consultants, some code consultants to build what now is a 240-page document that really lays out the plans of how to build very large buildings, up to 30 stories tall in wood, using this new system. We designed it very specifically around Vancouver, and we decided that our report needed to demonstrate that this was rigorous from a technical point of view, but also rigorous enough to show that it was cost effective and tell the story why consumers would want to buy it, why developers would want to do it, how people would ultimately market these ideas, and also obviously the other sort of critical parts of how they worked and what their sustainable story really would be. So in Vancouver, where I live, it's a high earthquake zone. We wanted to really challenge our system by building in the highest earthquake zone in Canada, by proposing it in that environment, and also proposing it in a dense urban environment and really work with contractors to understand how we would actually technically build something on that scale. So the system's actually remarkably simple. The first version of this I built with my son when he was 6, and we sat down on the ground together and put it together. Sometimes the best ideas are just that easy. And I sort of I work with some outstanding world-class wood engineers in Vancouver. I'm lucky. I come from a wood culture, and there's some outstanding wood engineers. I've worked with the engineers of this building in New York, and my engineers in Vancouver actually have been helping the New York firm understand wood a little more. We have a great culture for wood. And when I pulled them aside, I said, guys, my son Macalo and I have been making this, and I really think this is interesting, and this has some real potential to build big, and what do you guys think? And they sort of said, yeah, this actually works, and we started working on it more and more over the last 5 years until we reached this point where we realized that it's not only possible, it's actually really practical to do this, and it's shaken things up a little bit in the big conversation worldwide. Because this just came out 2 weeks ago publicly, it's kind of an interesting moment for me just personally and for our firm, because what's happened is, we spoke to CNN a week ago, and we're talking to Bulgaria newspapers, and some guy from Iraq contacted me about how to do this. So it's become a very quick and very instant conversation because it seems so different. The idea of, to get to 9 stories is astounding. To talk about 30 stories, obviously, is a very new paradigm shift for the world to get their head around. And ultimately, we think it's very realistic. Much like what Andrew just described, the idea is motivated by sustainable methods of building, these big urban buildings, but also it's about how we innovate for faster, lighter, less expensive, and better performing for the global scales of challenges. And those challenges, again, climate change, world housing, we've got to deal with them, because as we talk world housing, especially in the developing world, the issues kind of collide. If we build the way we're building today to solve that 3 billion people that need a new affordable home in the next 20 years, we are obviously going to significantly impact climate footprint, and we can't do that. There has to be a new way. So the system, as I say, is really simple, and in our case, we use a little bit of steel. It's effectively a 98% wood building. The elevator, like Andrew's building, the elevator cores, the stair cores are all wood. Using these mass timber products. But we use a little bit of steel, and the reason we do that is in a high earthquake zone, we need something that's ductile, that gives a little and sort of has a little more elasticity to it. And so we use the steel, ironically, as the weak joint in the design. So for anybody in engineering, this is a strong column, weak beam design. And what's interesting in the way we approach it is we had some of the best seismic engineers in North America do our peer review. And what's interesting is the technical way that an engineer analyzes our building is it uses the exact same software you would in concrete. So it's actually very easy for a lot of engineers to get their heads into how to do this. It's just using this very new material. The material, those mass timber materials that Andrew touched on, laminated strand lumber, laminated veneer lumber, and CLT, cross-laminated timber, have been around for a long time. 100 years ago in BC, if you wanted to build a fireproof wall, you took 2x4s and nailed them together, or 2x6s and nailed them together and made a massive solid wall. So when I renovate a building in my community, I'm often hitting a massive piece of wood, and the only reason it's there is because of fire. It's completely hidden in the wall. But what we know is massive pieces of wood actually resist fire and behave really predictably in fire, which is very counterintuitive to the way a lot of people feel about wood. But the difference is it's easy to light a fire with a little sticks to start it up. It's very hard if you start with a log and try to get it on fire. It's very difficult to get it to work. That's why the torches on the balcony weren't lighting up necessarily for when they were putting the waterproofing on. So just to kind of give you an overview, I'm not going to go into a lot of the detail of our report, but what we were trying to do again is say, it's one thing to have a good sustainable message, but what we know statistically is 95% of the public will tell you that they will pay more for something that is green, but only 5% actually do. This system, these ideas don't sell because they're good for the planet. That's not what's going to happen, even though luckily Andrew's building sold out with people with that attitude. That's not going to propagate the idea. So instead, we had to make this cost effective. Part of it was speed. And part of it was showing that it had all the same flexibility as any concrete building. So this is a concrete building. And what we did in our study was we actually looked at a 12-story concrete building, 20-story concrete building, and a 30-story concrete building. Every step of the way, because concrete's what we build with in Vancouver, not steel, every step of the way we would compare our wood system to a concrete system. No matter what the metrics were going to be, we would get a rigorous comparison. And what became really important in that was that in order to get developers to want to do these kinds of buildings, they want flexibility. And we wanted to prove that we could do this not just in residential buildings, but ultimately in office buildings. And in order to do that, you really want a building plan that's wall-free. It's just open, free plan. So that means in an office, you can lay out your office space however you want, and you can build, if it was residential, you can build your residential unit wherever you want. So in our system, we're using these large-scale panels, and we tilt them up, and they're 64 feet long if they're LVL or LSL, so they're 6 stories tall when you tip them up. And we're building up to 12 stories. We're building with glulam columns, just like these big beams here, slabs of these large mass timber panels, a central core and an elevator core made entirely of the timber panels, and some steel ledgers that help us again with the flexibility of the system. What we found is up to 20 stories, up to 12, we had this beautiful free open plan. You could have all glass exterior, which a lot of buildings are made that way. That's not the way hopefully we'll be building buildings in the future, because it's obviously terrible from an energy performance point of view. This gives the developers flexibility. Then what we found is if we move away from the columns and put solid panels on the exterior, we can actually get up to 20 stories. Or we could put brace walls inside, a little bit more like Andrew's building with a few more load-bearing walls on the inside. And ultimately, to get to 30 stories, we'd mix those two things, make a fairly solid exterior and walls on the inside. Since this diagram was made, we've actually been able to show that we can do option 2 and 3 here all the way to 30 stories, which means that we can make an office building 30 stories tall in wood. It means we can make a flexible plan for a developer to do a housing project in 30 stories, which is an extraordinary sort of result that we were truthfully a bit surprised by as we pushed the engineering further and further. So I'm going to go quickly now in this part. But as I said, what was important about our system was that we tested everything. So in this case, we actually met with construction companies, some of the biggest ones in Canada, and talked about how you would actually erect them. And for us, what was funny with that is that they didn't know who to bring to the meetings. This isn't something anybody does. Do we bring wood carpenters? No, because these panels are massive. This isn't wood carpentry. Do we bring concrete guys? No, because that doesn't make any sense. There really isn't a clear trade that actually builds this. It's probably closest to steel in some respects, because it's kind of a kit of parts that goes together, but it's in many respects kind of this big unknown because nobody's been doing it. But they were excited about it, and that was what was great. Is every single group we talked to, from contractors to developers to building code officials, were really A, intrigued, and B, after they learned and read more and understood what we were talking about, really all of the obstacles seemed to be slowly disappearing for us. Everybody was coming on side because the ideas seemed to be researched and understood well enough. And with the contractors, to our surprise, we basically are building up the central elevator core, bracing it, and building in lifts of 6 stories at a time. So you can see these panels. The elegance is basically, the simple way for everybody to think about it is a 2x4, the way we build small residential houses, has now become a giant piece of wood that's 8 feet wide and 64 feet long and 3.5 inches thick, and at times 7 inches thick, to allow us to get these huge heights. So again, without going into any detail, what I just want to point out is throughout our study, what we were able to do is compare concrete to steel, to wood, constantly back and forth, show how they worked acoustically, show how they worked in fire, show how they worked from a building envelope point of view. And our sort of study is filled with millions of these diagrams to really help articulate it. And one of the things that almost became a surprise to many people is that in concrete, a lot of the time we had thicker slabs or thicker walls than we would for the same building of the same height in wood. And the reason is quite simple. Andrew touched on it. A wood building is 1/4 to 1/6 the weight of a concrete building. So when you're building in a high earthquake zone and you build in concrete, as you go higher and higher, the mass of the building becomes very great. And the forces that you're trying to resist are very, very great because the building itself is so heavy. When you do it in wood, you're actually resisting less force. And what we found in a building that's 12 stories tall, in Vancouver, you would typically see the concrete walls around the elevator shafts be 1 foot thick. And in wood, they were only 9.5 inches thick. So it was almost a huge surprise to us that wood actually resulted in more floor space and a more simple system. So again, we went through systems and how they were integrated, and we went through all the different conditions of balconies. We don't need to spend too much time. And we wanted to check the boxes of the standard challenges. Currently, no building code has imagined these systems, so certainly the code is a big one, but really the issues are kind of consistent. Wood shrinks, and that's true, but when you build a very tall building, as wood shrinks as it dries out, the problem is you can have real technical problems with how that building goes together. In our system, if we built it on the right, the platform-based system where you build up to a certain height and then put a floor in, build up and put a floor in, it would actually result in adding up the floor slabs. And as you get very tall, that actually deals with a bit of shrinkage, although Andrew saw very little in his building at 9 stories. Once you're at 20 or 30, that can become a bigger issue. So what we've been working on is a system where the floors are actually sit in between and we don't absorb the shrinkage. And so it's really effective. In fact, it shrinks about the same amount as any concrete building would. So that solves some technical problems. I'm just going to keep going a little quicker now. So from a moisture point of view, just like in Murray Grove, in Andrew's project, we don't put the wood structure out there for the weather to beat it up. There's always an envelope that protects it, and that's a really important thing. I'm slowly learning all the issues that are the buzzwords for the public that write underneath the CNN article, all of their kind of concerns and complaints, and they're good comments. They're very standard comments, but there's also a lot that's just misunderstood, and there's no intention to build these things and have them sit out in the weather and rot and be exposed to termites and so forth. Those things are all taken care of. Acoustics is the biggest issue. Probably the hardest issue of all the things we dealt with is just that in a big building, concrete resists, the mass of the concrete actually is very effective at dealing with acoustic issues between suites in a building. And getting these buildings to work is very possible, but it also requires some pretty sophisticated detailing. And from a fire point of view, and Andrew touched on this a little bit, we have two systems. Big, tall buildings in North America have to resist a 2-hour fire. And what that means is whether it's steel, concrete, or wood, they have to stand for 2 hours so that the firefighters can get in them, people can get out of the building safely, firefighters can go in and fight the fire, and also the building doesn't collapse during that time and damage property or kill people down below it. That's just the way the codes work naturally, and to deal with that, we had to prove that we had an answer for 2-hour fire rating for a tall building. And the way we do that, there were two options. One is that we just cover everything in 2 layers of fire-rated drywall, and that creates a 2-hour fire rating with some very specific technical details of how we do it. And that's called encapsulation on the left. But the other that's more exciting, and for us in Vancouver, the building code authorities are really interested in, is something called charring, where we actually calculate the thickness of the material of the wood on the outside that will burn over 2 hours. And there's different calculations for it, but it's roughly 6 millimeters per minute. And if you calculate that, or sorry, 0.6 millimeters per minute. If you calculate that over a 2-hour burn, it's going to be about 2.5 inches, 2.75 inches of burn that you will lose of wood. And that assumes your sprinkler system didn't turn on in pretty much catastrophic conditions. As long as the structure, the meat of the material left over after that burn is strong enough to hold up the building, you've satisfied that 2-hour fire rating. And our codes in Canada, and I think here as well, around heavy timber, buildings like this actually have understood that for 100 years. And so because of the nature of these big panels, that's how we actually can solve fire at a large scale. So that's the sort of standard burn. I mean, in some parts of the world, we actually, which is fun, we actually protect steel construction with wood construction, which just goes to that counterintuitive reality that we need to change people's perception of wood. And really, ultimately, this is where we're at right now. We're at that next step of building it. And within the next few weeks, I'm hoping we'll announce in Vancouver that we're going to build a 20-story wood building, which will be the world's tallest for now. And hopefully somebody beats us real soon. Maybe it'll be Andrew in London. I think that's it, right? I think that's it for now. So we have, in our presentation, maybe we'll jump to questions. But what we also have are some other example projects. So if you guys are interested, we could also just show you some of our work, some of the places we're using, playing with these materials. Maybe we'll pull that up, and then at the same time, you guys can ask questions. Anybody got any?